An auction-based algorithm. We will present an auction-based algorithm for the linear case of the error Debreu model. It will find an approximate equilibrium in the following sense. For any fixed epsilon greater than 0, it will find prices P for the goods such that the market clears and each agent gets a bundle of goods that provides her utility at least 1 over epsilon squared times the utility of her optimal bundle. The algorithm initializes the price of each good to be unit, computes the worth of the initial endowment of each agent, and gives this money to each agent. All goods are initially fully unsold. We will denote by P equals to P1, P2, P3 until Pn the vector of prices of goods at any point in the algorithm. As P changes, the algorithm recomputes the value of each agent's initial endowment and updates her money accordingly. Clearly, at the start of the algorithm, the total surplus unspent money of all agents is n. At any point in the algorithm, a part of good j is sold at price pj and a part of it is sold at 1 plus epsilon times pj. The run of the algorithm is partitioned into iterations. Each iteration terminates when the price of some good is raised by a factor of 1 plus epsilon. Each iteration is further partitioned into rounds. In a round, the algorithm considers agents one by one in some arbitrary but fixed order, say 1, 2, 3 until m. If the agent being considered I has no surplus money, the algorithm moves to the next agent. Otherwise, it finds I's optimal good. In terms of bang per buck at current prices, say it is good j. It then proceeds to execute the operation of outbid. This entails buying back good j from agents who have it at price pj and selling it to I at price pj times 1 plus epsilon. This process can end in one of two ways. Agent I's surplus money is exhausted. If so, the algorithm moves on to the next agent. No agent has a good j at price pj anymore. If so, it raises the price of good j to pj times 1 plus epsilon by setting pj to pj times 1 plus epsilon. The current iteration terminates and the agent's monies are updated because of this price rise. When the current round comes to an end, the algorithm checks if the total surplus money with the buyers is at most epsilon times a mean. If so, the algorithm terminates, otherwise it goes to the next round. At termination, the algorithm gives the unsold goods to an arbitrary agent to ensure that the market clears. It outputs the allocations received by all agents and the terminating prices P. Observe, however, that some of good j may have been sold at price 1 plus epsilon times pj, even though the equilibrium price of good j is pj. Because of this discrepancy, agents will only get approximately optimal bundles. Lemma 5.25 will establish a bound on the approximation factor. Lemma 5.23, the number of rounds executed in an iteration is bounded by big O of 1 over epsilon times log of n times Pmax over epsilon times A mean. Proof. Observe that if outbid buys a good at price Pj, it sells it at price 1 plus epsilon times Pj, thereby decreasing the overall surplus. Therefore, in each round that is fully completed, i.e. does not terminate midway because of a price increase, the total surplus of agents is reduced by a factor of 1 plus epsilon. The total surplus at the beginning of the iteration is at most the total money possessed by all agents, i.e. n times Pmax. The iteration terminates, and in fact the algorithm terminates as soon as the total surplus is at most epsilon times A mean. Therefore, a bound on the number of rounds in an iteration is log with base 1 plus epsilon of the term n times Pmax over epsilon times A mean. Lemma 5.24, the total number of iterations is bounded by big O of n over epsilon times log of Pmax. Proof. Each iteration raises the price of a good by a factor of 1 plus epsilon. Therefore, the number of iterations is bounded by n times log of base 1 plus epsilon of the term p max. Lemma 5.25. Relative to terminating prices, each agent gets a bundle of goods that provides her utility at least 1 minus epsilon squared, 1 minus the square of 1 minus epsilon, times the utility of her optimal bundle. Proof: the algorithm always sells an agent her optimal goods relative to current prices P. Recall, however, that at the time of the sale, an agent is charged the price of 1 plus epsilon times Pj for good j. There are two reasons why an agent I may end up with a suboptimal bundle in the end. First, at termination, part of the money may remain unspent. Let M denote the total worth of I's initial endowment at terminating prices, assuming that she spent M1 of this. Since the total surplus money left at termination is at most epsilon times A mean, M1 is less than or equals to 1 minus epsilon times M. The second reason is that some part of good J may have been sold at price 1 plus epsilon times Pj to agent I, even though the equilibrium price announced is Pj. Equivalently, we may assume that I gets her optimal goods at prices P for a fraction of her money. The latter is at least M1 over 1 plus epsilon, which is greater than or equals to 1 minus epsilon times M over 1 plus epsilon, which is greater than or equals to the square of 1 minus epsilon times M, money. So the lemma follows. Theorem 5.26. The algorithm given above finds an approximate equilibrium for the linear case of the error Debreu model in time. Big O of Mn over epsilon squared times log of n times b max over epsilon times a mean times b mean times another log of the content b max over b mean. Proof: observe that each good whose price is raised beyond 1 is fully sold, since the total money of agents is the total worth of all goods at prices P. The condition that the total surplus money of agents is at most epsilon times a mean must be reached before the price of all goods increases beyond 1. Hence, at termination, the price of at least one good is 1. Clearly, at termination, the ratio of maximum to minimal price of a good is bounded by Vmax over Vmean. Therefore, Pmax is bounded by Vmax of Vmean. Each round is executed in a big O of M time. Now the bound on the total running time follows from lemmas 5.23 and 5.24.